Yes, this is the OSI model, and previous sessions we talked about at each layer of the OSI model, additional information will be appended to the original data, and if we're talking about the application layer, the additional information will be appended here. At the presentation layer, we have additional information appended in this area. Session layer, additional information is appended here. And at the transport layer, additional information is appended in this location. Well, we refer to the additional information as being a header. Now let's take a look at two header options at layer 4 of the OSI model. Okay, we could use the TCP header, which consists of source, destination port, sequence number, an acknowledgement, and then some other values as well. Note that there's a checksum field in the TCP header, and then if we make a comparison with the UDP header, we see the source, destination length, and also the checksum field. The checksum field is basically an error detection mechanism. The source device will compute a checksum or value based upon the source, destination, length, and put the checksum here. That's if we're talking about UDP. In regards to TCP, the checksum value will consist of source, destination, sequence number, acknowledgement, and all of the fields up to the checksum field. And the receiving device will run a computation of those fields and come up with a checksum value, and it will compare its checksum value with the checksum value stated by the sender, and if there is a match, then the packet will go on to the next destination. If there is a mismatch, then of course the receiving device will discard the packet. Okay, if the option is TCP at the layer 4 of the OSI model, then the communication could be considered as connection-oriented or reliable. And the reliability comes in play because basically an acknowledgement will be required of the receiver before the sender sends additional packets. Okay. In comparison to the UDP header, we don't see an acknowledgement field, we don't see a sequence number field, and we don't see some of the other fields. UDP is more streamlined protocol. It's designed for basically real-time type activities such as video, audio, any type of transaction in which you really can't afford delays. We can imagine there will be types of delay solely because of the acknowledgments required within the TCP header. Again, the TCP header has the sequence number. That affords the receiver the opportunity to reassemble the packets in the appropriate order. Most packets will go across the packet switching network. With that said, you could potentially send 1,000 packets, and each packet may take a different route to the destination. So if the packets take different routes, the packets may not receive in the order specified by the sender. However, if there's a sequence number associated with each packet, then the receiver can, again, reassemble the packets in the original order. Okay, TCP has another advantage over UDP. That is, TCP will check to make sure that the receiver is available before sending information. UDP does not do that. UDP just fires it away, and if it gets there, fine. If it doesn't, oh well. Okay, before TCP actually commits to sending data, it employs something known as a three-way handshake. And you may want to reference the three-way handshake slide that's in your textbook. Okay. Before the sender initiates the data transfer, the sender sends what's known as a SYN. Okay. And the SYN will include a sequence number. In this instance, we see that the control bit is being used, or there's a 1 in that field. Let's take a look at the control bit or the control flag. It's referred to by a number of terms. These 6 areas are known as flags, or some people refer to them as control fields. Well, when TC1 sends its initial communication, or step 1 of the three-way handshake, it's going to place its 100 value, the sequence number, in this field. And also it's going to set the SYN flag to 1. These flags or bits can have one of 2 values, either 0 or 1. A 0 indicates that that field is not used. 1, of course, indicates that that particular field or bit is on. Well, during the initial sequence number, in the instance of computer A, step 1 communication, the SYN flag is set to 1. This will indicate to the receiver that the 100 value is the initial sequence number for the communication. The sequence number does not have to start with 0. It can start with a value, let's say 2 million. And if that's the case, the receiver will not know that the 2 million is the lowest value or the initial sequence number unless the SYN flag is set, unless there's a 1 in the SYN field. Okay, computer A gets step 1 to computer B receives it, computer B sends what's known as a SYN ACK. It will place a 300 in the header sequence number field, and also it's going to place an acknowledgement value 101 in the acknowledgement field. Note also that the control bit or flag is used. So there's a 1 here. And also there's a 1 in the acknowledgement field. Well, the receiver, in this case, computer A, will see that the sequence number used by computer B is 300, and it'll also see that the control bit is set, so they'll know that 300 is PCB's initial sequence number. Okay. Well, why is computer B using acknowledgement number 101? Well, it's indicating to computer A that it has received acknowledgement or not acknowledgement, but sequence number 100, and it's expecting the next sequence number from computer A to be sequence number 101. Okay. All right, we go to step 3. We see that computer A is generating the next packet, and it's using the sequence number 101, which goes in this field, and the acknowledgement number uses value 301. Notice that the control bit for the SYN flag is not set this time. That's because this 101 is no longer the initial sequence number. Note that the acknowledgement number is 301, and it's going to be sent back to computer A, and computer A will look at this and realize that computer A did receive sequence number 300, and computer A is now expecting sequence number 301. Okay. After steps 1, 2, and 3 of the three-way handshake have taken place successfully, then the data can be transferred. And throughout the data transfer, the sequence numbers will be used as well. Sequence numbers and acknowledgement numbers. What happens if computer B sends sequence number 501 and does not get an acknowledgement on a certain amount of time? It's going to resend sequence number 501. What happens if computer B sends sequence number 501 and receives an acknowledgement from computer A, and acknowledgement number is 501? Then computer B knows that computer A did not receive 501 because computer A is expecting the next sequence number to be 501. So there again, computer B will resend 501. Hence, you see how this could be a problematic situation for a voice over IP communication that relies on the TCP protocol at layer 4. Imagine carrying on a conversation and packets are being delayed or withheld simply because acknowledgments are not being sent or received. So yes, we wouldn't want TCP. We would want to use UDP because it does not rely on the acknowledgments. And one of the beauties of using UDP is that, especially in regards to with using the voice or video, is that so many packets are being sent, and voice conversation and video data can be broken up into millions of packets. So the loss of one packet or packets may not distract from or may not distract the receiver's ability to interpret the data. Okay, let's say, for example, let's use this graph. There are thousands or perhaps millions of pixels being used to produce this graph. Even the white areas consist of tiny pixels, tiny white pixels. So we could imagine the loss of transferring, let's say, 100 of these million pixels to the receiver will not impact the receiver's ability to interpret the graph. However, playing devil's advocate, if this particular graph is composed of, let's say, 1,000 pixels, and the loss of 100 pixels occurred during communication transfer, then yes, in that instance, the loss of data would be quite impactful on the receiver's ability to interpret the information. Okay, to speed data transfer, TCP has the ability to negotiate what's something known as a sliding window size. Well, instead of devices expecting acknowledgement for each packet sent, they can negotiate a window size, which in essence, for example, specifies a range of packets to be received. An acknowledgement will be expected for a certain range of packets received. For example, computer A and computer B could decide that an acknowledgement will be sent after sending and receiving 1,000 packets.